Assalamu alaikum to everyone. Today's topic is solvent exchange mechanism, which is explained using kinetics and mechanism of a complex formation. So first of all, what is solvation? Solvation is the process by which solvent molecules surround and interact with solute ions or molecule, whereas a solvate is a compound that forms between a solute and its solvent. Like here we have a solvate compound, whereas the solvation number describe the number of solvent molecule bound to a solute species. For example, for the case of copper sulfate, we have 5 water molecules. These 5 water molecules are actually the solvated water molecules, or also known as solvate. And as this is water, then this is also known as water of crystallization or hydrate. So let's see, we have a metal ion which is surrounded by the solvent molecule, making a tight bond that is intermolecular bond. This intermolecular bond formed by the uh, solvent molecule which are directly at the surface of this metal ion is known as the primary solvation sphere, whereas this primary solvation sphere is producing a polarization effect that is spreading towards outward, making other solvent molecule to organize in a sphere known as secondary solvation sphere. In order to understand that this solvent can be replaced with other solvent when this solvation sphere is dissolved in another solvent. So let's take an example of a metal ligand complex. Here we have metal with n number of plus charge which is attached with 4 ligands, and we have a counter ion, and here we have a solvent molecule. This solvent molecule try to make a intermolecular bond with this metal ligand complex to generate an intermediate. Here we get a solvent attached with metal intermediate complex, and this solvent attached with this metal intermediate cortex. When you are talking about the primary and secondary solvation sphere, if we have a metal ion here, this metal ion is making 2 solvation spheres, but the next or upcoming solvent will make a bond with the secondary solvation sphere. So here we have an intermediate complex which is actually a secondary solvation sphere complex. So after making an intermediate, this secondary solvation sphere is converted to a new solvent metal bond with older metal ligand bonds. Here we can see that the solvent can replace the ligand, and the mechanism in which ligand is replaced by the solvent is known as ligand exchange mechanism. And here I have described one mechanism. This is known as ligand substitution, and it can be seen that it's like SN2 reaction, in which we have intermediate which is formed by attacking nucleophile and the substrate. In this mechanism, metal solvent bond is formed before the breakdown of the metal ligand bond. The mechanism is known as interchange through association, that is termed as IA. In this exchange through association or IA, we can see that in the intermediate complex, the number of coordination or the coordination number of metal ion is increasing. That it was previously 4 and here we have 5. So if we check the volume of the reactants and intermediate formation, here we have solvent and metal ligand complex, and here we have a metal ligand and solvent intermediate. So we can see that the overall volume of the system is decreasing. Why? Because the solvent and metal ligand these two fragments have more volume, because these two are species are separated and they are combining to make one intermediate molecule. Overall volume of the system and that is change in the volume is negative. Let's take another example. Here we have a metal ion is surrounded by 6 ligands, and for this case the metal ligand bond is broken down at first stage to make again an intermediate. Here we can see that in this intermediate there is a decrease in the number of ligands, and here then solvent will make a bond with this central metal ion in a solvent exchange mechanism or ligand exchange mechanism. As we are talking about the transition metal complex, so we can call it ligand exchange mechanism. Actually we are exchanging the ligands in a form of solvent, so we can also call it ligand exchange mechanism and solvent exchange mechanism. And here in this example, ligand and solvent both do not exhibit their own charges. So here we can see that this mechanism resembles to the SN1 reaction we have already studied in the organic chemistry books. So this reaction is known as exchange mechanism through dissociation. Why? Because the metal ligand complex, or we can also have a metal solvation sphere that is dissociated with less number of ligand or coordination number, then solvent is making a new bond. So if we study this method experimentally, overall volume of the system must be increased. That is delta V. Delta V should be positive. Why? Because if we have a metal solvation sphere or metal ligand complex, like in this case we have Ml6 that is broken to Ml5 plus L, and here we can see that the overall volume of the system is increased. It means that the fragments occupy more volume as compared to the original metal ligand complex. In both cases, we have seen that intermediates are produced, and these intermediates are important for the determination of the SN1 type or SN2 type, or it can be said that these two intermediates are describing either the dissociative or the associative mechanism of the ligand exchange process. For the determination of these intermediate, highly sensitive instruments are used which can detect the intermediates because they are short-lived and they exhibit very low energy differences between the products and the intermediate. For this purpose, ESR technique is used for the detection, that is known as electron spin resonance technique. And other technique is the volume change that is visible and which also give the most simple and accurate measurement for the detection of the type of mechanism followed by the solvent exchange mechanism. Let's take an example of nickel aqua complex and monodentate ligand here and describe the number of donating group. Here if this N is 1, then this is the monodentate ligand. So this ligand is replacing one water molecule in a forward direction, that is the second order formation constant for the formation of inner sphere complex, and the Kd is the first order dissociation constant as the process of ligand exchange is reversible. And for this example, both associative and dissociative mechanisms are observed, and overall dissociative mechanism is favored. Here we can see that the first one is the dissociative mechanism, in which an intermediate is formed with having less number of coordinated water molecule as compared to the original coordination complex of nickel, whereas for the case of associative mechanism, the number of coordination is increasing for this nickel, as the number of water molecules is 6 with the additional ligand in the coordination sphere, and these two processes are also reversible, and from these two processes we can calculate overall rate constants from the equation. Here the rate that is observed experimentally, which is plotted with respect to change in the concentration of nickel ion in the solvent. Overall rate of forward reaction and rate of dissociation is calculated from the slope and the intercept of the experimental rate constant change with respect to the nickel ion concentration plot. And for this case, if we replace the ligand with the bidentate ligand, which can donate two electron pairs simultaneously to a central metal ion of this complex, making a ring-like structure. And for this case, experimentally observed reaction was associative mechanism. We have observed that the mechanisms followed by monodentate and bidentate ligands are opposite to the trend usually observed for the SN1 and SN2 reactions. It's because here the strength of the ligand matter which determine the stability of the uh, metal ligand intermediate complex, and this intermediate complex is although sterically hindered, but here the strength of the ligand matter, and this strength decide that how These ligands can replace the water molecules. Here water molecules are acting as ligand, and the ligand is acting as solvent, which is exchanging the ligand of that is water molecule. SN2 mechanism, or the uh, associative mechanism, is usually favored for the stronger ligands, and as well as for the smaller size of metal ion, which are hard metals, having a higher polarization effect on the incoming ligands.